cos h of any value, being negative or positive, will always turn out to be positive. Now sin h of a negative value is negative, sin h of positive value is positive. Now since if the graph is bipartite, the negative values are the same as the positive values, the sum of all the sin h values will be what? 0. Isn't it? Because for every negative value there is a corresponding positive value among the eigenvalues. So if you take the sin h of those eigenvalues, for every negative sin h value there will be a corresponding positive sin h value. So the sum of all those sin h values will be 0.
Sir, I have a question.
Yes.
Cos h lambda, how we will calculate?
You have a calculator right now?
Okay, got it.
So these are radians, these are not angles. So if you have a calculator, let me see, I think I have here one. No, the scientific is not.
I think I have scientific.
But your normal calculator should have that. This one doesn't have. So try cos h of negative 2.
Cos h, okay, got it.
Okay?
Cos h,
Anything, just if you want to try.
it's coming like 0.999.
I'm trying to think something else. Cos h, you just did cos. Hyperbolic cos function, sine function. Okay, so if the sum of all the sin h values becomes 0, then this ratio is just sum of all the cos h divided by again sum of all the cos h, which will be 1. So, which means a bipartite index will be 1 if the graph is bipartite, okay, or truly bipartite. Okay. Now, so the curiosity is then what happens if the graph is not truly bipartite but it's close to being bipartite with some edges between vertices the same partition. So let us see another example. So this graph doesn't look like being bipartite, so we'll try to see how close it is to being bipartite. So again, find the eigenvalues of this graph. So from the eigenvalues itself, you can decide whether the graph is bipartite or not just by looking at the numbers, because they are not images of each other. If the graph is bipartite, then for every negative value it has a corresponding positive value, and so on. So we'll go ahead and find the cos h values and sin h values. Okay. So then sum all the cos h values, sum all the sin h values. So the formula for bipartite index is sum of all the cos h values divided by sum of all the cos h values plus sum of all the sin h values. So 35.2 plus 35.2 plus 8.08. So here the sum of sin h values is not 0. So that itself is an indication that the bipartite index is going to be something less than 1, because if this ratio has to be 1, the sin h contribution, sum of all the sin h values should be 0. So now the denominator is getting larger than the numerator, so the ratio will be less than 1. Now how close it is to 1, that's the indication of how close it is to being bipartite. Okay. So the properties of the cos h and sin h functions is like that. The smallest possible value of this ratio will be 0.5. Okay. So the bipartite index values will always range from 0.5 to 1. Okay, so 1 is like truly bipartite, 0.5 means it's not really anything to do with bipartite, it's like an arbitrary graph. Any questions so far?
Based on the most negative figure 5, it says negative 2 on the previous slide.
Based on what? This one?
On 1, 3, slide 1, 3.
1, 3. Yeah, I haven't come to that yet. I'll talk about so far what we did is, given a graph, we want to determine whether it's bipartite or not using the bipartite index. So if it's not bipartite, you can also have a feel of how close it is to being bipartite. So several researchers have tried to find, actually this researcher proposed this notion of bipartite index, Estrada. So he went ahead and actually tried to quantify the extent of bipartite of several real world networks. So you could see the minimum value is 0.5 and then could go to like 0.976. Okay. So none of the real world networks are really truly bipartite, but some of them are close to being bipartite. Okay. Now, how to identify the two partitions? We already did that with the breadth first search, if you remember, right? So if it's truly bipartite, we can what? Find out the two partitions, right? All the vertices with odd levels are in one partition, and all the vertices in even level are in another partition. Now, with the eigenvalue approach, we could also determine the two partitions. So let us pick now this example. So this graph is bipartite, truly bipartite. So the approach is this. Again, we don't need to know whether the graph is truly bipartite or not. What we'll do is just find eigenvalues and the corresponding eigenvectors. Pick up the eigenvector corresponding to the lowest eigenvalue. Okay. So this is the lowest eigenvalue for this graph. It's all the numbers, -2, -2, then -1, and so on. So -2 is the lowest eigenvalue, and this is its corresponding eigenvector. Okay. So just pick up the vertices that have positive sign for the entries in the eigenvector and negative sign. So all the vertices with the negative sign in the entries in the eigenvector are in one partition, and everything with the positive sign in the eigenvector or in the other partition. So here you see 1, 3, and 5 or the -0.4082, the eigenvectors. So it need not be always all the same values. Just for this graph, it's very symmetric. It turns out to be like this. We see another example. So here 1, 3, 5 are the same partition. Then 2, 4, 6 have positive entries, so they are in a different partition. So those are the two partitions. Is that clear? Okay, so just look at the eigenvector corresponding to smallest eigenvalue, not the largest, smallest eigenvalue.
Sir, here also the eigenvalue is came from like Gauss edge.
Eigenvalue is something that we find out of the program I gave you.
Yeah.
All right. Now,
So,
yes.
never mind, I answered my own question.
Okay. Now, so what if the graph is not bipartite? So the graph is not bipartite. So let me introduce this notion called frustrated edges. Okay. So if the graph is not bipartite and there are some edges between vertices in the same partition, there's a name for those edges. They are called frustrated edges. Okay. Now, it is the presence of such edges that actually lowers the bipartite index. You can see here, this graph is truly bipartite. So if you determine its bipartite index, it will be 1. But all the other graphs here are not truly bipartite because of the presence of such edges. Now, you may wonder why the bipartite index is different for these two graphs, even though they have only one frustrated edge. But if you look at more carefully, the frustrated edge here is in the larger partition, and the frustrated edge here is in the smaller partition. Smaller partition means few vertices in that partition compared to the other partition. So the property is this: if two graphs have the same number of frustrated edges, if then they could still have different bipartite index if the frustrated edges are in the smaller partition. They are going to have a lower bipartite index. If the frustrated edges are in the larger partition, they are going to have a relatively higher bipartite index. Okay? So, because basically, if you have the edges in a smaller partition, then it reduces the extent of bipartivity. Okay, there are only two vertices in this partition and this edge between them, so that's not that good. Okay. Now again, this graph has two frustrated edges. This also has two frustrated edges. Again, the presence of the frustrated edge in the smaller partition lowers the bipartite index more compared to this graph.
Sir, what is frustrated edges? Can you
Just edges between vertices in the same partition. So the graph is bipartite, such edges should not be there. Right? So like for this graph, there's no such edge between vertices in the same partition.
Okay.
Okay. So again, as you keep going, the bipartite index value decreases. So now for a graph that is not truly bipartite, we will try to find the two partitions of the graph such that the number of frustrated edges is minimum. Okay. So let's take this graph. We know it looks like it's not truly bipartite. So let us go ahead and find, and we found its bipartite index already to be less than 1. It came out to be like what, 0.8135. So let us see now how could we partition such a graph that is not truly bipartite into two partitions such that the number of frustrated edges is minimum. So we are not proving that, but the approach that we are using will give you the two partitions with fewer number of frustrated edges. So again, run the eigenvalues and eigenvectors and find the eigenvector corresponding to the smallest eigenvalue. So if you find the eigenvector corresponding to the smallest eigenvalue for this graph, the smallest eigenvalue is negative 2.487 something, and this is the corresponding eigenvector. So again, put together the vertices with the same sign. Don't look at the magnitude, just the sign, negative or positive. So 2, 4, 5, and 8 have negative sign in the eigenvector entries. So 2, 4, 5, 8 will form one partition, and the other vertices are positive entries, so they'll form the other partition. So this is the same graph. Oh.